All right, let's talk about using the Rydberg equation, and you know what that is already from our notes. The Rydberg equation says the energy of a photon is 2.18 times 10 to the minus 18 joules times 1 over n final squared minus 1 over n initial squared, where the n's here are the energy levels of the hydrogen atom, and in particular they're the principal quantum number for the electron in the hydrogen atom. Also, we can relate this to the wavelength of light of the photon because energy is equal to hc over lambda. So let's see how we use this equation, illustrating it with a few of our homework problems. So 7.69, according to the quantum mechanical model for the hydrogen atom, which electron transition would produce light with the longer wavelength? Longer wavelength, by the way, that's going to be the one with the lower energy, right? Lower energy will give you longer wavelength. And you can see that again from the Rydberg equation. If you've got a bigger lambda, a bigger wavelength, that'll be a smaller amount of energy. All right, now let's look at our two options. We got 2p to 1s or 3p to 1s. One thing to keep in mind is this p versus s is irrelevant, because that refers to the L quantum number. L equals 1 for P, L equals 0 for S. That doesn't matter. The only thing that matters, the only thing that's in the equation, are the n's. So here we go from n equals 2 to n equals 1 versus n equals 3 to n equals 1. This is going to be a smaller gap, 2 to 1 versus 3 to 1. You can see that too in the equation. If you've got 1 over 2 squared, 1 over 1 squared minus 1 over 2 squared, that's going to be a smaller number than 1 over 1 squared versus 1 over 3 squared. So lower energy for the 2p to 1s, so you're going to have lower energy for your photon, so you're going to need a longer wavelength for that. So it's the 2p to 1s. All right, let's take a look at 771. Calculate the wavelength of light emitted when an electron in a hydrogen atom makes each transition and indicate the region of the electromagnetic spectrum where the light is found. So here we've got N2 to N1, so similar to before. Here I've just rearranged the Rydberg equation solving for lambda. So lambda is hc over E photon. So I've got my hc there, Planck's constant, speed of light. And then here I have the Rydberg constant times 1 over n final minus 1 over n initial squared. So this really is just plug in the numbers once you've got the rearranged equation. You get 1.22 times 10 to the minus 7 meters. But you want this in nanometers, and so here's the conversion factor, 122 nanometers. We want to indicate the region of the electromagnetic spectrum where the light is found. Well, if we look in our text, here we've got the whole thing for frequency, and here's the whole spectrum for wavelength. Notice that the visible ends at 400 nanometers. We had 122 nanometers. So it must be just to the right or more energetic than violet, and that would be in the ultraviolet region. So that one's UV. All right, let's take a look at 7.75, ultraviolet radiation. Radiation of shorter wavelengths can damage biological molecules because they carry enough energy to break bonds within the molecules. We know that's true. UV light can give us sunburn, for example. A typical carbon-carbon bond requires 348 kilojoules per mole to break. What is the longest wavelength of radiation with enough energy to break carbon-carbon bonds? Well, keep in mind this energy is the energy per mole of bonds, but each photon is going to break just one bond, so we need the energy for one bond, not per mole of bonds. So 348 kilojoules per mole, we can convert that to joules. And then we know that there's a mole of bonds for every 6.022 times 10 to the 23rd bonds, Avogadro's number there. So moles of bonds will cancel, and you end up with joules per bond. It's a small number. We wouldn't expect much energy is required to break just one chemical bond. Alright, so we've got the energy per bond now. Now we need to know what's the longest wavelength. Well, again, if that's the energy that we need, we can rearrange to solve for wavelength. Wavelength is hc over E. Planck's constant, speed of light, divided by, in this case, we've already figured out the E, the energy from before, and just plug in the numbers. You get 3.44 times 10 to the minus 7, or 344 nanometers, which again, that is in the UV spectrum. 344 will be to the right of violet, so ultraviolet, just like the problem asked us, ultraviolet radiation. Alright, let's look at 781. Ionization involves completely removing an electron from its atom. What does that mean, completely remove an electron? How much energy is required to ionize a hydrogen atom in its ground or lowest energy state? So the initial state must be n equals 1. So we're going from n equals 1 to ionization. And then what wavelength of light contains enough energy in a single photon to ionize a hydrogen atom? Okay, so we know n initial is 1, because that's the ground state. Where does it go to be ionized? Well, it has to go all the way to n final equals infinity. That's the furthest away you can get from the proton before you're totally disassociated with the proton. Well, then we can plug these two numbers into our Rydberg equation. So the energy of the photon, 2.18 times 10 to the minus 18 joules times 1 over 1 squared minus 1 over infinity squared. Well, what is 1 over infinity squared? There's probably no infinity button on your calculator, but maybe you know this from a previous math class. If you divide by infinity, you get 0. So in fact, we just have Rydberg constant times 1, which is just the Rydberg constant. Okay, you need to find the wavelength of the light, and I think I'm going to leave that to you guys to figure out. If you know the energy by now, you should be able to get the wavelength.